Hi, I'm Jacob. Thank you very much for coming. Today I'm going to be speaking about ReasonML. I'm really excited to talk about this. I've got a lot of good content. I hope everyone gets some really good stuff out of it. I go home at the end of the day looking like this a lot. And the reason that I look like this is that writing correct software is really hard. But it's really hard doing it in a language that has no real formal semantic understanding of what correct software actually means. So I spend a lot of time writing JavaScript, a lot of time writing Ruby, a lot of time writing dynamic programming languages. And in languages that don't have a strong type system, it's very difficult to actually express whether or not something is correct. So what we're going to cover today is how using a language like Reason can actually improve your developer experience, improve your day-to-day experience, improve the quality of the software you ship, and improve your confidence in the product that you're actually delivering. So how many different implementations do you think you could write for the function that's on the screen? So the function should read as an as-yet unnamed function of any possible type A that returns any possible type A. With such a breadth of applicability, there are no restrictions on the input type. The only restriction on the output type is that the value is of the same type. Such a breadth of applicability, how many functions do you think you can write? Well, if we constrict the solution space to functions that definitely respond, definitely return, don't loop forever, don't throw exceptions, and we agree that we're going to be pure and have no side effects, there's only one implementation. There's only one thing you can do. And the only thing you can do is return the exact same type that you were given at the beginning, the exact same value you were given at the beginning. And the reason for that is you actually know nothing about the type. You know nothing about the information that is being passed into the function, which means you can't actually assert any behavior that is legal to perform on that type. From a correctness perspective, your hands are tied behind your back. This was a very, very confronting thing for me the first time that I came across it, that having restrictions on the input types for a program could actually grant you more freedom, and having absolute freedom on the input types of a program was very constricting. But what I think basically made me realize that, and made me kind of understand that, was looking at the kind of code that exists in a lot of the dynamic systems that I work with. So a lot of the code looks like this. We have a lot of very, very well-named variables. We have a lot of checks for the types of the values of the things we're dealing with. And we have to rely on things like commenting or documentation to explain to us why the function is doing the thing that it's doing. We don't have static analysis. We don't have compiler safety. We begin to rely on runtime exceptions for control flow to help us kind of differentiate between the ways that we are programming. And I think the reason that we do that is a lot of the time, languages that give us compile time safety, languages that give us static analysis, are painful to use. They require us to write annotations in every variable we define, or they're not safe themselves, and it just becomes a pain, and we don't get any trade-off or value for that. But what if there was a way to get a strong compile time static analysis safety in your program without giving up the things that make programming in a dynamic language fun, where you don't have to write a type annotation on every single variable in your program, where you don't have to deal with the difficulty of null checks at every possible function open? What if this language was available to you now to use? So the language that I'm going to introduce is called Reason, ReasonML. And Reason is a language, well, it's a syntax and a toolchain, effectively, defined over the OCaml language. OCaml is a functional programming language. It's probably about 20-something years old, long history in academia and in industry. And Reason is being developed by Facebook as kind of an introductory functional programming language for people who wouldn't have come across these concepts otherwise, born of recognizing that the barrier to entry with OCaml was higher than most people were willing to climb over to get to the benefits. So the other really interesting thing about Reason, and what positions it for me today, is that it actually compiles really, really well to JavaScript. So that makes it very, very compelling for general purpose programming. As someone who works on the web, if I can't compile to JavaScript, I can't actually do anything in a browser. I'm stuck with static HTML being sent back from a controller. It's difficult to work with. It's very difficult to explain to a product manager why you might want to downgrade your experience because the correctness of your backend system is important. By having something that can compile to JavaScript, we get the best of both worlds. We get all of the dynamism on the front end, and we also get complete compile time safety at compile time, effectively. A lot of the things I'm going to discuss today will be very, very general functional programming benefits There are a couple of things that are specific to Reason and to the bucklescript compiler, which is the compiler that we use to go to JavaScript. But the vast majority is just functional programming techniques or typed programming techniques. So we'll start by discussing the ways in which a backend system might be maybe not as safe as you might like it to be. And this is a really important topic for me because, from my perspective, the backend is the really, really important bit of a web system. It's the bit that's connected to your source of truth. Presumably, it's connected to your database. And in the end, what that means is, if that isn't correct, if that isn't reliable, then you really have no way to be comfortable that your system is performing what you'd like it to. And it's very important to me that a backend system be correct. But they are so seldomly so. So back on the JavaScript theme, this is a controller from the expressiveness HTTP framework. And this is a pretty common piece of code that I see in a lot of different applications that I've worked on. We have a controller that takes a request object, a response object, and a next object. And it checks to see if the body contains a variable, and if it does, it responds. But there's an error here. There's a really, really big bug here. Can everyone see the bug? The bug is that if the body is null, we throw an error and don't respond. Or if the body doesn't contain either of the variables we're slicing off it, we throw an error and respond. Which means that there are a number of code parts that are completely valid from JavaScript's perspective that might occur in our system that we don't protect against, and that nothing is helping us be aware that we don't protect against. We have no tooling or no information that actually helps us know, hey, you probably want to cover these other cases. You haven't, and that might lead to incorrect software. We have a house built on foundations of straw rather than stone. So what can we do to improve this? Well, the first glaring issue is that JavaScript's return types don't actually exist. There's no such thing as a return type for JavaScript because there's no type system, which means asserting behavior from a static analysis perspective is very difficult. It's very difficult to know, looking at a piece of JavaScript code, what is the actual return type, what is the actual input type for this. So let's look at what we might do to improve that situation. And we're going to set a very, very strong kind of constriction on ourselves. Every function we deal with should take arguments, and at the very least, it must return a meaningful result so that we know the type of the response of the function, so that we can assert the behavior of the function, so that we know more about it. So we're going to look at what it means to use the Express backend from inside Reason. So we're going to define some of the foreign function interface bindings using the bucklescript compiler. And we're going to define them so that we can call the JavaScript that Express exposes from inside Reason, but do it in a type-safe manner. So initially what we do is we describe an abstract type done. An abstract type is a type that doesn't have a constructor, which means it can be returned from something but not created by itself. We then define 4 modules, and we'll go into the definitions of those modules. We define request, response, next, and middleware. Request, response, and next all apply to the types that we saw before, the rec, res, and next types. Middleware is the definition of what a controller, of what a middleware in our system is going to look like. So in this case, we see what the initial definition of what a module looks like as far as Reason is concerned. A module in Reason, we'll get into much more detail later, but for the moment you can think of a module as a namespace in which types and values exist and will not clash with types and values in other namespaces. They're a process for allowing us to encapsulate behavior without clashing on different named functions. So we define the 3 modules, request, response, and next here. We give them each an inner type T. You'll see that they have type T in a lot of modules in Reason and in OCaml. It's completely a convention for what the main type of the function is, but it doesn't actually mean anything special. It's just there is a type T that is available. The request object is very sparse for this example. The response object has our first example of a bucklescript external binding. And what that is we have the call to send HTML. And what we do with send HTML is we actually compile that down to a JavaScript statement that says the first argument you give this function is going to be the thing that we call send on. The second argument you give this function is what we're going to call send with. And we're going to return from that done. So this is the first function that we can see in our system that can actually produce a type of done for us. We say that when send HTML is finished being applied, we're done in the controller. We also define our next module. So our next module also has a type T. This time, next, that's really creaky. Next type is not abstract. It actually has a constructor. And we see that next is a function. It's a function that takes something that might be nullable and returns are done. So we now have two ways in our system to actually return done. We can either say something went wrong, and we call next with a potential error, and let that flow take place. Or we say everything worked as we expected to, and we're going to send HTML back to the client. So we're now ready to define a middleware in this system. And we say that a middleware is something that has a type T, where we have a request.t, a response.t, a next.t, and we return done. So this is the really, really important bit of this system. This is the bit that I really like. We guarantee at compile time, with no exceptions, that our middleware function absolutely responds to the client. And the way that we know that is the only functions in the entire code base that can produce done are send.html and next.t. Nothing else can do that. Because of that, we have compile time safety, compile time assurance, that we absolutely, no matter what else we do inside a controller, respond to the client. So this is what it would look like then to construct a middleware of that type. We define a function f, and f we see takes three parameters, rec, res, and next. And we have a switch statement. So this is an introduction to a really cool concept called pattern matching, for anyone who's not familiar with it. Pattern matching can be thought of similar to like an if statement. But where an if statement operates on values, pattern matching operates on types. So it allows us, in the same way that an if statement can check what the value of a variable is, and say perform this code branch if it's 1, perform this code branch if it's 2, a pattern match looks at the types. In this case, it looks at the algebraic data type, the optional type, and we're basically saying, if we have some computation that returns none, consider that an error, and respond to the client that something has gone wrong. And if we have a response from our function that is sum, if something's gone right, take the inside of that and respond to the client in the appropriate way. So we match on the actual construction of the value rather than on the value itself. And what we can see here, the really interesting thing looking at this is there are no type annotations, right? There's no boilerplate. There's nothing that gets in the way of us just defining our functionality. So we don't have to actually write type annotations. The compiler can infer them from how these functions are used. In this case, by passing it into the app.get function, the compiler goes, cool, app.get takes a middleware is of type middleware.t, that means rec is a request.t, res is a response.t, and so on. The responsibility for actually determining what is going on belongs to the compiler, not to me, because I'm nowhere near as smart as a compiler. The responsibility for helping the compiler when it gets confused now is only ours. But that lifts a whole bunch of responsibility off our plate. And it helps us hugely identify that the only paths that we now need to write tests for are the insides of controllers to make sure that our business logic is correct, that they respond with the correct data. We don't actually ever need to care again, do all of our controllers respond? Do they catch errors? Do they handle problems? Do they do any of the things? They definitely do. The compiler assures us of this. The compiler not only assures us of it in the happy path, but it also helps us when things go wrong. So in this case, we're pattern matching, and we're saying, for every sum that occurs, respond. But we're new to the code base, and we haven't yet learned what the business rules are, and we don't really know why something might return none. So we say, when it returns none, log it, because I'd like to check it out later. But logging is not the same as responding to the client, and the compiler will not let that happen. It absolutely will not, which protects us from doing things that maybe we don't know well enough not to do. We don't have to have 100% knowledge of the code base. We can actually push into the type system the rules around why the code base is structured as it is, and then rely on the compiler to protect not only us, but people who are new to our projects to help them write correct code. So we've seen a way to improve our back-end system by using the type system to help us write correct code. Let's take a look at the front end. So I have somewhat of a love-hate relationship with front-end programming. I think I probably only really started to enjoy it when React was released. And a big reason for that was front-end programming for the longest time has been slung with very much abandon. It does not really have a concept of correctness. And a big reason for that is that JavaScript, the language of the front end, is not correct. Fundamentally, it is a very difficult language to write correct code for. And you can see this in a lot of the efforts that have been created, and they are admirable efforts, to provide static analysis for JavaScript. The Flow, TypeScript, Closure Compiler, these are all very powerful tools, and a lot of effort has gone into helping us write safer JavaScript. But they each have to make trade-offs to allow code to run that is valid JavaScript code, but that is not valid correct code. So you'll see Flow, for instance, unifies types that are unwrapped. So you can have a value that is both a string or a number or null, and the compiler doesn't care, Flow doesn't care. That's a totally valid state to be in. From a correctness perspective, that is very difficult to deal with. So what we're going to look at now is, instead of trying to write JavaScript correctly, let's rather focus on, I want to say that this particular part of my program should be correct, and I'll deal with the fact that I write JavaScript in other parts and let that be as correct or incorrect as I can get it, but I'm going to compile to JavaScript this other bit. So the framework that I'm going to describe this in is React. Are there any people who use React in the audience? A sea of hands. Probably not super surprising these days. So React, as I mentioned before, React is developed by Facebook, obviously. Reason also developed by Facebook. And interestingly, Reason was created by the same person who created React. So Jordan Walk was the person who came up with React initially, and Reason was also created by Jordan. And then, more interestingly, React's initial prototype was actually in standard ML, which means that by bringing our React bindings back into Reason, we've come full circle. We find ourselves back in the ML promised land. So we're going to go through a little bit about how we can structure a React code base in Reason and what the benefits of that might be. So initially, to start with, we're going to deal with just a hello world example. We have a greeting component. For anyone who's not familiar with React, this is a function, effectively, that will take some data and respond with some HTML. That's effectively the computation that we're performing. And we see here we have a render method that just takes the prop that we were passed and returns it. The other thing we can see is that we have this static member, prop types. Prop types is a dynamic runtime evaluation of the types that are passed as arguments to a React component. It's the way that in vanilla JavaScript, we assert whether or not the values that we're passing obey the contract that we've written to make this component hierarchy work. And this is the method that we rely on when we don't have flow, or we don't have static analysis, or we don't have a language with these semantics built in. But as with all dynamic runtime evaluation techniques, we have to trace every single pathway of our program in order to know whether or not we've actually hit all of the bits that we care about. These things run at runtime, so we don't have any real easy way to tell, is this actually safe everywhere? Does this obey the contract that I want it to everywhere? Unless we trace each of those paths dynamically. So this is one of the drawbacks with using just pure prop types, and one of the drawbacks with using just JavaScript. It's more or less manageable when you have a very small project, more or less manageable when you can keep the state of your entire application in your head. As soon as you have anything larger than that, it's very, very difficult. We find ourselves at the mercy of our time or our tooling. And in a refactor or in a crunch, these are the kind of things that tend to fall by the wayside. We're OK with that linting error. We're OK with that prop type error. We don't really mind. We'll come back to it later. And we never come back to it later. So what can we do? Well, looking at how Reason treats React, Reason, as we've seen up till now, is a strongly typed functional programming language. And ReasonReact components are just strongly typed functions. So in this case, a ReasonReact component is just a module, like I said before, a namespace, that has two members, a component and a make function. And the make function is the thing that is analogous to a React component, to a React stateless functional component. It's effectively a function of some props that returns something that produces HTML. And what we have here is we see our greeting component from before. We define it as taking a message property and a children property that we're ignoring as far as the body is concerned, because we don't use it. And we take the component that we've defined by calling ReasonReact stateless component, and we spread it apart. And we override any of the defaults that we want to override to change the behavior. So now we have a fully functional React component. So this is the record syntax from React. Anything within curly braces by itself is a record. A record is something that has very particular properties. It's effectively an object with predefined properties and values. And what we're doing here is we're saying component comes back with a number of these properties, but we want to override the render property. And that's what we're going to use to produce HTML. So here we have a way of doing something a little bit more interesting. We now want to say that we want some kind of dynamism in our system. We want to have some state. We want to have some interaction. And ReasonReact is fairly unique in that it allows you to compartmentalize that state at any point in your component hierarchy, at any point in your tree. The way that it does that is by a concept called a reducer component. And you'll see from ReasonReact, that's the function that we actually use to create the component variable this time. So a reducer component is an ordinary React component that has some state and has some methods to allow you to update that state from anywhere in your tree, from anywhere in your subtree, rather. And so on rendering this component, we can generate a number of callbacks and pass those callbacks to be used in response to actions that might take place. And then when those actions take place, we call those callbacks and have the effect of that be that the state updates, causing a re-render again, and we update the subtree. So the way that we do that is we first define a type for action and a type for state. The action is the actions that we want our reducer to be able to operate on. So we say that we're going to listen for clicks and we're going to listen for restarts. These aren't magic terms. These are completely arbitrary. What I'm going to do later is attach those to a click event. We also have some type of state, which is, again, just a record. And in this case, we say that state is a clicks counter, which is an integer, and a restarts counter, which is an integer. We define our reducer component using the ReasonReact reducer component function. And then we override some default properties on that. We override the initial state function, the reducer function, and the render function. So we override the initial state function to say, initially, give me back a record where clicks are set to 0 and restarts are set to 0. This now gives us the time to override those. It gives us the position to override those. We then define our reducer function as something that returns an update to that record. And you'll see that the shape that it returns is exactly the same as the initial state shape, exactly the same as the state shape. We have an action that we take in, and we have the current state of the application at the time that reduce is called. We then switch, we pattern match on the action that's occurred. When we've hit a click, we want to update the click counter. We want to leave the restart counter exactly as it is. When we hit a restart, we want to set the click counter back to 0, and we want to increment the restarts counter. So this is the way in which you handle set state effectively, the way that you handle state propagating through your system. Equally then, the way that we bind this into HTML, we attach the functions that we have available to us to the HTML nodes to handle the events, and we interpolate the state into a string so that we can show that. For anyone who works with Elm or anyone who works with Redux, this should look very familiar. The interesting thing is that as for the ReasonReact bindings, you don't actually need a state library. Out of the box, it does everything that Redux does better and with compile time safety. You actually know ahead of time, I don't accidentally listen to an action that I don't know how to handle. Everything that's in my reducer is also produced. Everything that's in my actions is also part of my reducer. There's no impedance mismatch. Everything is handled for you by the compiler. A couple of statistics on using ReasonReact on the front end. So the messenger.com website, Facebook's messenger website, is at about 50% conversion for the front end. A complete build of the system using the BuckleScript compiler takes about 2 seconds. An incremental build takes about 100 milliseconds. The amount of time it takes to type check every single statement inside your codebase is faster than you can even say the word unit test. Total bugs introduced over the course of a year, 10. Which is incredible. It's a great number. And the idea is that by having these correctness checks hit us at compile time, we never discover them at runtime. We discover them all while we're actually working on them, which means we don't worry so much about what the correctness state of our system is in production. We're much safer at compile time. So we've shown that the ReasonReact API protects all of the things we like about React. It gives us all of the same dynamic features that we enjoy about writing React, without any of the drawbacks of what we would consider a static analysis system would be. It augments our dynamic code with compile time type checking, which is very valuable. And it also helps us share or compose or refactor these components without having to worry, did we change something somewhere that we didn't track? So the refactoring is the bit that I really, really like about this process, about the inference. I find that like I mentioned before, I don't write very many type annotations. I'll only write them when I'm working in a library. But in the actual implementation of the code, you just write code. You don't write type annotations, which is really nice because you don't necessarily have to think up front completely what is the bare minimum type that I want to support here. But when it comes time to change or refactor, you don't then also have to read through all of the other code in the code base to go, well, I changed that, now does it change and break anywhere else? The type system keeps track of that for you. It helps you refactor. So I actually have my wife to blame / congratulate for this slide. She taught me the word philep. about 4 or 5 years ago. It's an Afrikaans word, and it's really fun to say. Philep is a really fun word to say. But it means like wilted or limp. And that's effectively how I feel about validation being done in JavaScript on the back end. Validation is a very, very important, data validation is a very, very important thing to perform. When we have data coming in from an untrusted source, knowing that it obeys the business rules that we have set for that data is very important. Again, source of truth, backend, these things are kind of vital. But one of the things you don't have in a dynamic language is the ability to know everywhere that I persist data, did I first validate it? So this is the data structure that we're going to pass around. This is what we're going to use as an example for what it means to persist or validate data throughout our system. We have a person, and a person is defined as having a name and an age. And we set that the name is a string, we set that the int is the age is an int, and this is the data structure that we'll use. If we were going to deal with this data structure from JavaScript, we'd have the data structure come in from some source, we'd pass it through a validate function, it would come out the other side of that validate function, we would check the results. If something went wrong, we would say, cool, get rid of it, throw an error. If something went right, we'd pass it on to save. But like I said before, we don't have any way to know every time someone calls save, did they first call validate? Every time someone calls process, did they first call validate? We don't have anything to help us at compile time check for these problems. So the way that we tend to deal with this is we either very tightly couple these operations into an ORM behind the scenes. So we have some private Boolean property is valid, and the ORM will set that property before it saves, and that will then, if we try and save something before it's valid, it will automatically call validate. We can call validate beforehand, and it sets whether or not it's valid. But it very tightly couples the behavior of validation to the concept of a persistence layer. But there are other things we might want to validate. There are other things that we might want to deal with. And we don't have a good data structure or a good safety assurance that we've done this thing. As a side note, did you know that Reason was haunted? So I'm speaking of phantom types. Phantom types are a type declaration where the types on the left-hand side, or the variables on the left-hand side, don't appear on the right-hand side. So in this case, we have type T of A equals string. The polymorphic A doesn't appear on the right-hand side. What does that mean? Well, we have type T of A as string, and we can now define that X and Y are both strings, but we say that they're really T of int and T of float, which doesn't really affect how we can use X and Y. We can still concatenate them together using the append operator, and when we log out the result, we still get foo bar. Nothing's changed. So at first glance, this seems like kind of a wacky, esoteric technique for just kind of mucking around with the type system. But if we couple that with the opaque types that we've seen before and modules, we actually get something really powerful. So before I show how we're going to use them to protect validation, I just want to go through what the API we'd like to have is. So we'd like to have a way of saying that a person validator will produce a person, but any operations that rely on that person being validated before we do that operation to them, we must make sure that we go through validate first, at compile time, not at runtime. So we see here that we have an introduction to the pipe operator. The pipe operator is just a way of taking an expression on the left-hand side and inserting it in the tail position on the right-hand side. And we can see here that when we do person validator make name age, and we try and save it directly, we should fail. At compile time, we should fail. When we have person validator make name age, we pass it through validate, and then we use the option fmap to say, if it's none, return none. If it's some, perform this operation. We should succeed at compile time. So what does that look like? This is a pretty big example. I'm going to break it up into smaller pieces. But the idea is that we can define some module interface, some module type, to say these are the bare minimum things you need to define to be considered a validator. And then we can define some implementation of that. And we can say, cool, this is how I am a validator, and this is what I validate with. The important thing to note here is that in the validator type, in the module type person validator, the type of T is abstract. In the implementation, the type of T has a constructor. Effectively, what this gives us is an opaque type. It gives us something where from within the module itself, we can reference the person constructor, but from outside the module, we have no way to do so. And the powerful thing with this is it means that no one, unless they use the methods exposed by the module, can construct a person. which means the only possible way to get a person is to go through all of the exposed public interface of the module. So let's go into what that means and how that's useful. So we have a module type person validator. We have two opaque types, valid and invalid, or two abstract types, valid and invalid. And then we have a type T of A, T polymorphic in A. We then define a method make, and we say that make, from the type perspective, is something that takes a string and an int and returns a T invalid. So we saw before that you can define something as coming back T polymorphic entirely, and we can say then because T is polymorphic entirely, the make function responds only with things that are T invalid. We then see the only function that we ever define that takes something from T invalid to something of T valid. We say that validate is a function that takes a T invalid and returns with an option T valid. We use option here just for the ease of the demonstration. In a practical system, I'd probably use either or result to capture why something went wrong. But in this case, basically what we do is we say if it's invalid and our validation checks fail, return none. And if it's valid, return some of a T valid. Finally, we see the method that we're going to use to show that the validation check will fail at compile time if we try and sidestep it. In this case, we're pretending that there's some save method we can call that'll take a person and put them into a database somewhere. So let's have a look at what that actually kind of looks like. First, we'll touch with the happy path. So we take a person, hi, me, and we pass them through validate, and then we pass them through option fmap, and we save them. Because the person obeys all of our validation rules, the construction happens correctly, we get back a T invalid. We then have a T invalid that we pass through validate. The validation succeeds. We get back a T valid. We can then pass that to our save method, which takes a T valid and returns a T valid. All of this works. What if we have someone who's too young? So from our validation perspective, we say that we don't want to store people in our driver database who are under the age of 18. We have someone who is very clearly under the age of 18. So we pass them through validate. Validation fails. We returned a none type. So from the option algebraic data type, we get back the none constructor. When we hit option fmap says, cool, you have none, don't worry about it. This is all still legally valid. It's all correct. We don't actually hit the compile system yet. But we receive someone who's none. We don't try and call save with none. We just let that go. What if we do something a little sneaky? So what if we then take person validator, we create a person, and then we try and just save them directly? So we can see that we actually get a compile time error. So this is where the phantom types really shine, is the fact that we receive a T invalid from make, and the fact that we've said that save works on T valid, means at compile time, we are assured that we never ever call a function expecting T valid with a T invalid. Really, really valuable. And we can see that. We get the error, T invalid is not compatible with T valid for save. Then similarly, if we do something really, really sneaky, and we start with not valid, and we try and cast that to a valid, taking advantage of what we think we know about the system, where we know that it's a person on the other end. Maybe we can just automatically cast it to a T valid. They're all kind of the same concrete type on the other side. But again, the compiler says absolutely not. Error type T valid is not compatible with type T invalid returned by make. You cannot cast between types like that. So there is no way in our system, no way at all, to save this object unless it first passes through validate, and we are assured at compile time that there is no way that someone has done this. The really interesting thing about this is when we look at the implementation, there is no function that makes use of valid or invalid. Make doesn't mention T invalid, validate doesn't mention T valid, save doesn't mention T valid. They all just kind of do stuff. The interface will basically set that type is T valid or T invalid, but from the implementation's perspective, none of that exists. And the reason why that should be interesting is that we have an understanding now that our friendly ghosts don't actually exist at runtime. There's no wrap-unwrap penalty for using this technique, which is really powerful. We have no runtime penalty for compile time gating the behavior of our system. We have a huge assurance that our system is operating the way that we intend it to, and we know that we can do this performantly. So this is very important. This is very useful. So we've seen that there are very, very strong things that we can do to push the behavior that we'd like to have up into our type system. The important thing to note here is that we haven't actually asserted anything in the type system about what our validator does. It just validates. we don't know whether it validates correctly or incorrectly from our business rules, and we should unit test that. But we are freed from having to assert that every validator is called before save. We're freed from having to trace every single controller and service path through our application to say, did I, in this path, call save before I call validate before I call save to get it into the database? So these are the decisions that it takes away from you needing to make. Finally, I'll end on some of the things that I think are really fun about the language. One of the things that I try and evaluate a language on when I first start playing with it is its ability to express abstractions. I really like abstractions just kind of for their own sake. And in this case, Reason isn't found lacking. So the first one that we'll touch on is modules. And we've spoken about modules a couple of times. Modules are actually the most widely used abstraction feature in Reason. Kind of cheating. And the reason it's kind of cheating is that every single file in Reason is actually a module. So when you create a file and you write some statements inside a file, the compiler at compile time will wrap all of the statements inside that file up, store them inside a module, and expose the module based on that file name. So you never have to worry about leaking into global scope. There's no way to actually pollute. There's no way to collide. The only place you can collide is within the construct of a file, and the compiler will tell you, hey, maybe you didn't want to do that. So these are the premier code organization and reuse for the language. And the way that we can get a feeling for that is we define a module type, which is an interface for a module. And we basically say that we're going to define some add, and we define a type T, and we define the type for an add function. And then we define an implementation for ints and an implementation for floats. So for an int, we're going to say that add is x plus y. For a float, we're going to say that add is x plus dot y. And this is a Reason thing or an OCaml thing where ints and floats are actually completely different types. But doing this, we can now see that we have a very common interface that we want to deal with. And I'll touch on what you can do with common interfaces in a second. But the bit that I want to show now is that, much like Ruby, modules are actually mix-inable and openable, which means they give us a very, very nice tool for sharing code in between different places. So in this case, we define a module which uses the float implementation. It locally opens it, which makes all of the methods defined on the float module available, but it doesn't expose them outside of the module. So if you then use this module, the user's float implementation module, you can't actually access the float operations from outside of that. They're only available locally. Similarly, we could use the include keyword, and the include keyword will take that module, take all of the properties and methods and values and types defined on it, and actually make those available to the module and make those available to consumers of the module. So we have mix-ins and we have code sharing. The other thing we have is that modules are first-class citizens of the language. You can actually pass them as values to functions. And as I said before, files are just modules, which means you actually have first-class files. You can pass files to functions, which is a really interesting idea. But so what we've done here is we've defined a type monoid. We've said that a monoid is something that has a type T. It has a function, it has a value mEmpty, which is whatever the base value of the monoid is. It has a function mappend, which takes two monoids and kind of squishes them together. And then we define a function mappend list. We say that mappend list takes a module M, takes a list of A, and will fold the list, applying mappend for every value of the list, starting it with mEmpty, and iterating the list. We have a little bit of type system trickery here. We say that we have a type A, which is effectively like a for all A. The way that module types work is they're basically constrained inside the module. They won't leak outside of the module scope. So we cheat a little bit and we say we have some type A, and I promise you the module that we're including, its T is the same as type A. I promise you the list that we're using is also of type A. So the module type and the list type are exactly the same. It's all cool, don't worry about it. And that's enough for the compiler to say, yes, I can restrict this to things that obey that type. And so this is how we can write kind of general first-class functions that have different behaviors based on what we pass into them. So rather than having to write mappend list for addition, multiplication, division, any of the operations we can perform, instead we define mappend list once for things that give us an mappend and an mEmpty. And then by defining things that are built the same way that mappend, built the same way that the interface is, we can just pass them into the function to produce new values or new functions. So in this case, for add, we sum the elements of the list, and for multiply, we multiply the elements of the list. So this is a very powerful feature. Finally, before I close up, we'll touch on module functors. This is a really unfortunate overloading of a term that is pretty much loved by every functional programming language, functors. A functor classically is a way of mapping from one category to another. In Reason, a module functor is a way of mapping from one module to another, which is why they were named what they are. So we can see they're not fmap functors. They're not a way of defining fmap. They're a way of taking an input module of a certain type and then extending it and adding new code to it to return an output module of a certain type. They're code generation facilities, similar to type classes in Haskell or templates in C, generics in general. They're a way of generating new code. So we can see that what we're actually going to do is we define a module functor. It's a module. It has some type input, some type output, and it uses those to restrict what we're going to map between. And then we define the functor itself, which is the make module. And the make module actually just looks like a function, right? It's a function of one thing that returns another thing. When we're done, we end up with a new module that obeys the type of the output. So the first thing that I did when I learned about this, like anyone who's tried to use Haskell before, I thought, well, I'll just write all of the Haskell type classes in functors. That'll be fun. And you can actually get really far. You can actually do quite a lot of them. There are a few things that you can't express or can't express easily, but for most of them, most of the ones that you actually want, functor, applicative, monad, etc., you can get all of those out of this. So what I'm going to do is I'm going to describe how to write mappable. And mappable is just the name we're going to use so you don't hear me say functor every 5 minutes. We're going to avoid overloading that term. We're basically going to say we define an input, which is of type T of A and fmap. We define an output, which is of type T of A, fmap, and also generates the infix fmap and the left fmap functions out of the fmap function. And we can see that our implementation here takes the input fmap and says infix fmap is just fmap, don't worry about it. And also says that left fmap is just basically taking your fmap function, but applying const to it and taking a value. So we basically say, for every single thing that we fmap over, don't return the thing that's inside the functor. Don't return the thing that's inside the mappable. Return this value. So when we want to define now the interface or the implementation for a certain type to be considered mappable, we define a module, which is we do anonymously here. So we have mappable.make, and next to mappable.make, we apply an anonymous module, where we set type T to be option. We define fmap to be from none to none, from some to some fx. And now we can use option, and for free, we get the definition of infix fmap and left fmap, completely for free, just because we know how to define fmap. We can generate all of the code here without needing to write it explicitly for every possible implementation of this type. So that's what we would use functors for as compared to module interfaces. The downside to Reason's abstraction system at the moment is that it doesn't give us ad hoc polymorphism. It doesn't give us things like type classes. What it means is we explicitly have to write functions that we want to pass these things into. We also aren't able to escape scope, which means that polymorphic modules don't behave quite the way that we'd like them to. There are two techniques that are used to kind of get around this. One is available now. Jerome Yallop and Leo White, I believe, worked on a paper, Practical Higher-Kinded Types, or Lightweight Higher-Kinded Types, which exposes a way to use something called defunctionalization, which turns ordinary modules into higher-kinded. It's a whole thing, which I'm not going to go into, but it's a really cool technique, and you can use it now. It's also actually available for Flow and TypeScript from a guy called Julio Canti, I believe, to have that same ability of higher-kinded types inside Flow and TypeScript. Really cool. The other way is the same people are working on a new OCaml compiler that contains something called modular implicits. And that'll give ad hoc polymorphism effectively to the language and allow you to use a lot of the same features, a lot of the same benefits. But until then, you end up having to use functors to kind of mimic the idea of being able to have this generic implementation code in a lot of places. So one of the only puns in the presentation, to take a reasonable approach, we basically, for every single logical branch, we test twice. If you nest a logical branch, you test 4 times. If you nest again, 8, and so on. How many times in your code base do you write unit tests that assert the types of the input or the output are valid? Worse than that, you can only ever really test the things that you remember to test. Unit tests only exist when you remember to write them. But you're then at the mercy of your memories, at your tooling or of your time. And as I said before, these are the things that tend to fall by the wayside when we're rushing, when we're pushing really hard, and we never come back to them. Types cover many of the things that we write unit tests for, and with a really powerful type system, you can push a lot of things up into the type system to cover that off. They're faster than unit tests, and they run automatically. Reason was born of excitement. It was born of excitement to introduce functional programming to web development. It was born of excitement to teach new developers these ideas that they wouldn't have had introductions to otherwise. And it was born of excitement to help give us these safe-by-default building blocks for the web. The last couple of years in web development have been years of tooling fatigue. The weight and depth of the amount of information, of tooling, of books, of conferences that you have to go to or be aware of just to be able to ship a production application. If you think that the number of monad tutorials on the internet is approaching too much, have a look for how many different ways there are to architect a Redux application. It's really a lot of information out there. Reason instead ships a rock-solid, pragmatic approach to delivering an application, and it does so intending to improve the developer experience and to reduce the cognitive load. So what if instead of writing software the way that we've been writing it for the moment, we push all of the complexity down below the language stack, we cut the churn, and we give ourselves some room to focus on the things that really matter. If this has been interesting, please come talk to me afterwards. I'd love to chat. If anyone wants some help getting set up, come find me. I'm getting really good at setting up the Reason toolchain. Come and join the Discord room. There's a lot of really friendly, helpful people in there who would love to help you out. And check out the Getting Started guide on the website. Basically, to get started using this is about 2 minutes of work, so it's pretty easy to just get up and running. And if you'd like to get in touch with me, that's probably the best way to do it. Thank you very much.